Chapter 20, part 2. Let's take a look at this example, potential for two charges. At location A and B, find the total electric potential due to 2-point charges. So we have a positive Q here and a negative Q here, and we want to know what the potential is at these 2 points, point A and point B. These distances are each A, they're equal. So we know what the potential is. Potential is the potential energy per unit charge, okay, or per unit charge or the per test charge, in fact. And when we did a little bit of a calculations, we found that this is in fact KQ over R for a point charge. So we found that it is KQ over R for point charge. All right, so if I want to find for A, the potential due to plus Q, I would have K plus Q over R, which is A in this case. And at the same point for negative, at the same point A for negative charge or negative Q, I would have KQ over distance, which is 2A. 1A here, the other A is here, is 2A. Okay, and this Q is negative, so I have to keep the negative sign. Remember, we include the negative sign when it comes to this. So at point A, V total potential, so V of the due to these two charges. So I have KQ over A negative or minus KQ over 2A. So V of total, I can factor out KQ over A. Now I have 1 minus 1 over 2. So I have KQ over 2A as my final answer at that point. For point B, for point B, okay, I have a positive charge being 2A away from point B. So V, because of the positive charge at point B, is KQ over R, which is 2A. And I have a negative Q, which is 1A away from B. So V, because of a negative charge at point B, is KQ over A, but this is for a negative charge, so I have to remember that I have to apply the negative here. And V total then is V of positive B plus V of negative at point B, one for the positive charge, the other one for the negative charge, which is KQ over 2A plus negative KQ over A. If I factor out KQ over A, I would have 1 over 2 minus 1, which is KQ over 2 with a negative sign. So in other words, if you want to find the potential at the point due to different point charges, you have to add them up. You have to find them individually and you have to add them up, okay? These are scalar quantities. For the negative charge, you have to consider the sign. So let me put a star here for, we have to consider the sign of the charges. okay? Let's take a look at another example. And I'm not going to solve this example completely because it will take a very long time, but I'm just going to direct you on the solution. So we have the magnitude of each of these charges is Q 8.6 times 10 to the negative coulomb. Okay, so all of them are equal. They have different signs, positive, positive, negative, positive. And the lengths of the rectangle, one is 3 centimeter, the other one was 5 centimeters. So I have 3 here and I have 5 here, okay? Find the magnitude of the electric field at the center of the square, okay? So we want to know what the electric field is at the center. We know what the electric field is, right? It is K Q over R squared, R hat. This R hat means it is in the R direction, okay? It is in the distance direction. So if you have a point charge Q at this point with a distance R, the electric field is along the R direction. So that's this R hat means that it's along the R direction, all right? Either going out of the charge or going in, either away or towards the charge. For positive, it's going out. For negative, it's going in. Okay, so we want to know what it is at the center. So at the center, what you have is this. You have a positive charge, which is causing this E to be in this direction, a negative charge, which is causing this E to be in the same direction, a positive charge, which is causing E to be in this direction, and another charge, same amount, which is causing E to be in this direction. These two will cancel out. They are in the opposite directions. They are equal because the charges are equal. The distance is equal. They are in the different directions, opposite directions. They will cancel out. Okay, so they will cancel out. We are left with two electric fields, E1 and E2, both in one direction. At this point, the electric field is coming out of the positive. At this point, the electric field is going inside the negative. So we have two charges, two electric fields, both with the same magnitude, both in the same direction. So we have to add them up. In other words, the E total at the center is E1 plus E2. Why? Because they have the same direction. Okay, and they are in the same value. Okay, so the E1 and E2 are the same value. In other words, if I want to find one of them, I have in fact find the other one. So E total is just if I find one of these electric fields and I multiply by 2. Okay, if that's the case, that made everything much easier for me. So E is 2 times the electric field of one of these charges, which is KQ over R squared, okay? And this will be along the R hat direction as well. So what I have here is then E is so E is, here we go. Okay, so I have E being 2, K is 9 times 10 to the power of 9, Q is given 8.6 times 10 to the negative 12 coulombs. So 8.6 times 10 to the negative 12. And R squared, the distance squared, distance from one of these charges to the center. So we're looking for this. Okay, and in fact, this is r. If this is r, this is the half of the distance of the total distance. So in other words, we are looking for this. This is 3. Oh, this happened again. All right, this is 3. This is 5. And this would be 4. So Pythagorean theory is telling us that if you're looking for this side, all you need to do is to do 3 to the power of 2 plus 5 to the power of 2. Okay? So this was a little bit inaccurate. If I want to calculate it correctly using the Pythagorean theory, I have it like that. Okay? So x is, this is x. One side is squared, the other side is squared under the square root. So I have 9 here. 3 to the power of 2 is 9. 5 to the power of 2 is 25. And x is under the square root 25 plus 9, which is 34. And this will be close to 5, but not exactly 5. So the value for that is 5.8, okay, right here. Now, when you're looking at this, we are at the center, so we're in the midway. So our r here is x over 2, which is 5.8 over 2, okay, which will be 2.9. So r squared here is 2.9 squared. And let me see if this is centimeter, because if it is centimeter, then we have to change it. So yes. So if that's the case, then I would have to change the centimeter back to meters, all right? So I have 2.9 times 10 to the negative 2 centimeters to the power of 2. And then whatever this is, that would be your E in the middle of this rectangle. Let's look at B. What is the force felt by the charge on at the lower left? So this charge. So when you're considering doing B, let's see, we have a form of positive charge here, negative charge here, positive charge here, and a negative charge here. So what it's doing is that, this is also positive. What it's doing is this, that this negative and this positive will attract, okay? And then, so I want to call it F1. And then these two will repel because they're both positives, which I want to call it F2. And then these two will repel as well, which I want to call it F3. But the fact is F2 has the same value as F3. Okay, so F2 and F3 are equal. Let's real quick go ahead and calculate that. You have F2 being equal to F3 and being equal to K, Q1, Q2 over R squared. And they're all equal. The Q's are the same for them. So what you have is that it is equal to K, Q1, Q2, they are both Q, they are equal, so I have Q squared, R squared, okay? So you have 9.9 times 10 to the power of 9. Q is 8.6 times 10 to the power of negative 12, okay, coulomb, to the power of 2, because they have a power of 2 here. R squared, R is this distance, which is 3. And this distance is 5, so they are not equal then. If that's the case, then I have to go back and show that they are not equal. We were calculating one of them correctly, but they are not just equal. So let's talk about F2. F2 is K Q1, Q2, R squared. So F2 is K. Both Q's are the same. They have the same value for K. So I have Q squared. Both Q's are the same. Both charges are the same. So you have the same value, R squared. So F2 is K, 9 times 10 to the power of 9. Q squared, 8.6 times 10 to the negative 12. And R squared, which is 3 centimeters. So I have 3 times 10 to the negative 2 to the power of 2. That's F2. Okay. Let's talk about F3. F3 is K, Q1, Q2, R squared. Okay. So 9 times 10 to the power of 9. Q1, Q2, they're the same, so it's Q squared. So I have 8.6 times 10 to the negative 12 to the power of 2. And R squared is this distance is squared, which is 5 squared. But this is 5 in centimeters, so I have to have 5, 10 to the negative 2 to the power of 2. Then you can calculate what this one is. F1, okay, is K, Q1, Q2, R squared. So 9 times 10 to the power of 9. Q squared, which is 8.6 times 10 to the negative 12 squared. Okay, and then the distance is this distance, which we calculated already. X is 5.8. So it is 5.8 times 10 to the negative 2 centimeters. I turn it to meters by doing that to the power of 2. Then they are all, you can calculate them. Okay. Now, what we have here is that we have 3 forces. Okay, we have 3 forces, F2, F3, and F1. So F2, F3, and F1. The most important thing here is that these are not along the X and Y directions. Not all of them are. So if I consider this being X and this being Y, F2 is along negative X, F3 is along the negative Y, but F1 is not. So I have to get rid of F1. In other words, I have to break it to its components. So what I would do, I would say that let's call this angle theta. Okay, so F of total along the X direction is F1 of X minus F2, and F total along the Y direction is F2 of Y minus F3. Now, what I don't know is this. I know F2, I know F3, but I don't know F1X and F2Y. Sorry, this should be F1, F1Y. So F1X is F1 cosine of theta, and F1Y is F1 sine theta, okay? So we know the value for F1. That is the value for F1 right here. Okay, put it in the calculator to find it. Now we know F1 for both cases, but what the cosine is, cosine of the of this angle, okay, you have three here, you have 5 here, you have almost 5.8, a little bit more than 5.8, but we can call it 5.8, and that is your theta. Okay, so based on this, I can write cosine and sine. Cosine is 3 over 5.8, and sine is 5 over 5.8. Okay, now what you have, if you do that, you will find f1 of x, f1 of y, and then you can put it here to find a total value for those. Okay, once you do that, your total F, total force, is F total x to the power of 2 plus F total of y to the power of 2 under the square root. Okay, because if you consider having an x direction and a y direction, x direction and y direction, then this would be your F total x, and this would be your F total y. Okay, part C is asking find the electric potential at the center of this rectangle. It is the same concept. Remember, we have to consider the sign of the charge. So if you have a negative, you have to consider the negative. V is KQ over R. Okay, for positive, you use positive. For negative, you use negative. And then you add them up. So in other words, what we have here is this. V at the center is V due to charge 1 plus V due to charge 2 plus V due to charge 3 and plus V due to charge 4. Okay. Now when you're looking at this figure, for all of these positive charges, the distance is the same. Okay. For the negative charge, distance is the same, but it is a negative. All right. So if I want to consider this, I have V at the center being equal to KQ over R for the positive charge, KQ over R for the second positive charge, KQ over R for the third positive charge, negative KQ over R for the only negative charge that we have. Now, these two will cancel out. Okay. So you are left with 2KQ over R. So you have 2K is 9 times 10 to the power of 9. Q is 8.6 times 10 to the negative 12. And R is the distance, this distance, okay, which we found it already, 2.9 centimeter. So I have 2.9 times 10 to the negative 2, turning it back to meters here, okay? So that would be the total value that you would have at the center, because these two cancel out because one of them is negative. So equipotential surface versus contour maps. So when you're looking at this, for example, this is a map of the mountain. It has been divided to areas with a certain height. So for example, all of this green area here have a certain height, right? Which is 50 meters, or this line here, okay? They are at a certain height. So when you're looking at this map, you're basically distinguishing different parts of this mountain based on its height. So all of this area would have the same height from the ground. In other words, they are having the same potential energy, because gravitational potential energy, because gravitational potential energy was U equals mgh. Okay, we have the same concept. Equipotential surfaces in electric field, okay, or in electric potential. Surfaces where the electric potential is constant, so they have a constant value, all right, and no work is done by a net electric field to move the net charge along the equipotential surfaces, okay. So there is no net work is getting, because if you remember, V was U over Q. Okay, so delta V was delta U over Q. Okay, and this delta U was negative W, or negative work. So I could write delta V being negative W over Q. But if it is an equipotential surface, that means there is no delta V. Okay, so that means that this guy is 0 because it's equipotential. So because V of A equals to V of B. So that means there is no work. So means no work is getting done on an equipotential surface. So as the radius gets larger, for a point charge, for example, the potential of the surface decreases. The electric field is perpendicular to each equipotential surface. Let's take a closer look. So if I have a charged particle at the center, these arrows are showing the direction of the electric field for me. Okay, as I'm getting closer to the center where the charge is located, I'm having more density of the electric fields, and thus I am having a stronger electric field when I'm closer to the charge. Now, if you remember the potential, electric potential for a point charge, V was K Q over R. If I have a point charge here at the center, if R is the same, that means this point and this point with for the same R would have the same potential. This point with the same R would have the same potential. This point with the same R would have the same potential. All the points, if R is constant, then the V is constant. Okay, so all of the points in a circle, all of these points that forms a perfect circle around my charge would have the same potential because R is constant. So if R is a constant value, then V is constant. Okay, in other words, it forms a circle around it. This point have the same R as this point, so the potential in these 2 points would be the same. This point would have the same potential because the R is the same. Okay, but as you go further away, as R increases, the V decreases. Okay, so because if this R is going up, then your voltage or your potential is reducing or decreasing. Okay, so these white circles are called equipotential surfaces, and they are perpendicular with respect to the field lines. Okay, so these are perpendicular. We are making an angle of 90 degrees. Okay, these angles are 90 degrees. So here's what it looks like. If you're closer, the R is less, so you have a higher potential. If you're further away, the R is high, so you are in the region of the lower potential energy. And these are the electric field lines coming out of a positive charge. We know that it's coming out of the positive and going to the negative, out of positive and in to the negative. Okay, we know that. So if I have a positive charge here and a negative charge here, we know what the direction of the electric field is. It's coming out of the positive going into the negative, But then these are the equipotential surfaces inside inside this point. And I think that there is a lab associated with this that you can find the equipotential surfaces and draw it. So these equipotential surfaces have the same potential. So a point here and a point here and a point here would have the same potential, all right? And a point here would have the same potential energy and potential. So because V is KQ over R for a point charge, but when you have two charges, the electric field would be looking like this, and it would have the same, it would have the same or 90 degrees angle with respect to the equipotential surfaces. So they don't like that. This is another example for the 2-point charge. If they are both positives, the surface would look like this, okay? So you have positive, the field lines are coming out of the positive. You have positive, the field lines are coming out of the positive. But if you have both of them at the same time, then you will have this configuration for your electric field lines, okay? Now the equipotential surfaces are surfaces with the same potential energy or with the same potential. All right, and these are these green lines, and as you can see at each point, the field and the equipotential surface would make an angle of 90 degrees with respect to one another. At each point of contact, they are making an angle of 90 degrees with respect to one another. This is the same exact example that we had in our last slide. Is again, negative, the field lines are going inside the negative, positive, the field lines are coming out of the positive, so look like this. Equipotential and electric field lines. Now let's challenge this idea, why it has to be perpendicular with an angle of 90 degrees. So why must an electric field be perpendicular to the equipotential surface? So let's suppose that E, which is right here, as you can see on my screen, and the equipotential surface, which is this surface right there, so this surface right here is the equipotential surface, are not perpendicular to one another. So in fact, they have an angle like, let's say theta, right here, okay? They have an angle. There would be a component of E, so this E would have two components, one in this direction, okay, E of Y, and one in this direction, let's call it E of X. E would have a component along the surface, and the charge would move, thus work would be done, creating a change in potential. Okay, one more time. This would cause a component of E being along the equipotential surface, and this will cause a charge to move, thus it requires for work to be done. And when the work is being done, it will change the potential, because we know that work is negative change of the potential, or work is Q0 times delta V. So if work is getting done, then the surface is not equipotential anymore. If this work is not zero, then this delta V is not zero. So we don't have an equipotential surface then. So in other words, if we have an equipotential surface, then we do not have any work, and the field lines are perpendicular with respect to the equipotential surface. So we have 2-point charge. At which point does V is 0? We are not asking if they are equal to one another. We're asking which point is 0. It's actually fairly easy. What was V before? K, Q over R for a point charge. These are 2-point charges, okay? Plus Q and negative Q. And for a positive, we have a positive value here, okay? For negative, we have a negative value here. okay? For positive, we have positive. For negative, we have negative. And so if I consider point C, this is R, and R is the same for both of them. Q is the same for both of them. K is the same for both of them. So you'll end up with negative. So you'll end up with 0 potential. If I consider that this is being my point, this would be my R. This would be my R. R is the same. Q is the same. K is the same. Their signs are opposite. One is positive KQ over R. The other one is negative KQ over R. So they'll cancel out. So at all of these points, the V is 0. Conductors as equipotential surfaces. So an ideal conductor, we know that inside the ideal conductor, the velocity, the field lines are 0. The field, or E, is 0 inside. So we know E inside a conductor is 0, okay? An ideal conductor is an equipotential surface. Therefore, if two conductors are at the same potential, the one that is more curved, that means it's smaller, will have a larger electric field around it. This is also true for a different parts of the same conductor. So let's take a look at this. I have a large sphere, okay, a conductor sphere with a radius r, okay, and I have a smaller sphere with radius r over 2, or half of r, but they have the same electric potential, okay? They have the same electric potential. What was the electric potential for the point charge? K Q over R. If this V is the same for both of them, okay, but R is different, that requires to have a different Q in order to keep the V constant number. So one more time, R is different. In order to keep the V, or the voltage, or the potential, a constant value, I have to change the Q to keep this ratio being constant. So if R is high, Q should be low. Or in other words, this ratio should be constant. This ratio, the ratio should be constant. Okay, so if R is changing, Q is changing. In other words, these positives are different. These number of positives in here on top of on the surface of this smaller sphere would be different from these positive on the surface of the bigger sphere. So this ratio is the key here. If R is big, you need a bigger Q. The total number of these Q's on the surface would need to be more to keep the same value for potential. If R is small, you have a small radius, then it requires to have a smaller number of charges on the surface to keep the same value for V. But since these charges are different, then the electric field would be different. It's the same as this one. For example, I have one shape here, okay? So this is the equipotential surface. Anything in this surface is equipotential. They have the same amount of potential in this surface. So lower charge density, low electric field. High charge density over here has a meaning of high electric field. We use this electric, potentials, or anything related to electricity, not only in science, but also in medical science, okay? So for example, this is the electrocardiograph that, shows the number of heartbeats, or, it shows the heartbeats for you. And the way that it's been doing this is that since your heartbeat your heart has some, and any parts of the body, in fact, has some electrical activity associated with it. So this device can show the pulse, which is the peak of the electric activity inside the heart, which is exactly at the same point when it's, pulsing. We have the same thing for brain. So all of these neurons in our brain are firing, and we can see those fires as the electricity, and we can map it and see the activity of the brain. So in almost last part of our chapter, we talked about chapter 20, we talked about capacitors. So a capacitor, and by the way, this is a very basic form of a capacitor. We have different types of capacitors. A basic type of capacitor consists of two conducting plates, one up here with the positive sign and one down here with a negative sign. So we have a positive Q here and a negative Q here, that are separated in the constant distance or the same value, which is D here, or this displacement for them is D. And then the area for each of these plates is A. Okay, so I have if I want to draw a 3D format of that, that would be one plate, and then this would be the other plate. Okay, one being positive Q, the other one being negative Q. Okay, and they are separated by a distance D. And this area, okay, this area is A for both of them. And this is a form of a conductor because there is an electric field inside from positive to negative. So that's your electric field right there. If you consider that, then the capacitance is the amount of charge, okay, to the potential difference. So these two plates have a potential difference between them. One is positive, the other is negative. So they have a potential difference, like 12 volts or 13 volts or whatever the potential difference is, okay? Now, the capacitance relates the charge to the potential difference. In other words, if you want to find the Q is the capacitance times the voltage difference between the two plates, okay? And the capacitance has the value or the units of Q, which is Coulomb, okay? So let me actually change the color because it's important. And V is just the voltage, which is V, or the potential, or volt. And we call it farad, or F. Okay? Let's take a look at this question about capacitors. We have capacitor C1 is connected across a battery of 5 volts. An identical capacitor C2 is connected across a battery of 10 volts, which has more charge. So C is Q over V, as I said, and then Q is CV. Okay, C is a constant value. It's a capacitor. It's the capacitance of the capacitor. Okay, so this one is constant. This value is constant. So if you change this V, which is the voltage, then your Q would be different. So if you change V, then Q should change. So Q1 is C1 V1, okay? So Q1 is C1, V1 is 5 times 5, okay? Q2 is C2 V2, so Q2 is C2 times 10, But I know that they are identical, so I know C1 and C2 are the same. So Q2 is 2 times Q1. Right, so which has more charge? Q2 obviously have more charges associated with it. So C2 has more charges inside. So again, about the parallel plate capacitors, this is very basic view of a capacitor. We have different types of capacitors. Area A, or a plate with area A connected to the positive with a charge positive Q. Plate area with an area A connected to the negative and has a negative charge, negative Q inside, and there is a field line, a uniform field line inside the capacitor. So as I mentioned before in chapter 19, this is uniform. Okay. Now, if you want to find the capacitance of this capacitor, that's the formula. Epsilon 0 times A over D. Epsilon 0 is the permittivity of the free space or vacuum, which is 8.85 times 10 to the negative 12 F over M. A is the area of one of these plates. Okay, so this A is the area of one of these plates, not both of them, just one of them. So this is the area of one plate. Okay, and D is the displacement between the two plates. So that's how you find the capacitance of a capacitor, if you're a polar plate capacitor, by the way. So if you're looking at this, if you increase A, then your C will increase, or your capacitance will increase. And if you decrease D, you will have the same thing. In other words, if you want to design a capacitor, if the displacement of these two plates are smaller, then you have a higher value for the capacitance. And if you are designing it in a way to cover more area, so you have a bigger plates, then you have a bigger capacitance, okay? In other words, we have it here. The capacitance increases as the plate becomes larger and decreases as the separation increases. So let's take a look at this question. What must be done to a capacitor in order to increase the amount of charge it can hold for a constant voltage? In other words, so what we have here is a constant voltage of 12 volts being connected to these two plates. Separation is D, the distance is D, and one of them is negative, the other one is positive, and the area of these plates are A. So what we can do is to do either A or B. Increase the area of the plates, which is A, because we know that the capacitance is epsilon 0 A over D. So what I can do is to increase the A, okay, or decrease the separation between the two plates. So the answer is D. Varying capacitance, number 2, it's another example. A parallel plate capacitor initially has a voltage of 400 volts. So initially had a 400 volts connected to it, and it stayed connected to the battery. So it will not be, removed. If the plate spacing is now doubled, what happens? So let's take a look. So what we have is this. We have C being epsilon 0 A over D. Okay, A is the same, the area. Epsilon 0 is the same. The D is doubled. Okay, so the C has decreased. So D is decreased. Sorry. When you double the distance, when the spacing is doubled, you have increased the D or distance, and thus decreasing C, or capacitance. D is going up in the denominator, C is getting lower. And then, so Q is C times V, right? If C is getting down, if C is getting lower, as you can see right there, because this D is changing, but you're still connected to the same value, so this is a constant number, okay, then that means this guy is getting down. This guy is getting a lower number. So Q is decreasing. Okay? The charge decreases right there. We have something called dielectrics, and these are used, most of the industrial capacitors are, or the capacitors that we use mostly are having dielectrics inside them. So this picture A is showing you a capacitor without a dielectric inside, but a dielectric is a form of insulator, okay, non-conductor materials that you can put inside the capacitor to increase the capacity of it. Okay, once you put this insulator inside the capacitor, all of these particles inside will be deformed. Okay, so as you can see, this negative here, all right, will be going towards the positive. Negative will go towards positive. So all of these negatives are going along, are being attracted towards the positive. And these positives are also being attracted towards the negative. So the molecules inside this dielectric is getting deformed because you have one side being positive, one side being negative. Then this molecule is deformed like that. Okay, so not only you had before an electric field from one side to the other, but you have this microelectric fields inside as well. Okay, now an electric is an insulator, as I said. When placed between the plates of a capacitor, it gives a lower potential difference. Okay, it gives a lower potential difference with the same charge due to the polarization of the material. So all of these materials, all of these electrons, protons that are forming the molecules inside are getting deformed, or they're getting polarized. Okay, this increases the capacitance. Let's see how it does that. So the polarization of the dielectric results in a lower electric field within it. The new field is given by dividing the original field by the electric constant K. So this dielectric has a constant, which we call it K. Okay, and E, the new one, is the original without the electric field divided by K. Okay, so therefore the capacitance become this V. Okay, remember that E is V over D. Okay, now it is E0 over K is V over D. Okay, now this is the new voltage. Okay, so what I have is V of the new one is the V of the old one without the dielectric between over K, and this is the dielectric constant. but then you can bring this dielectric constant, which is currently in the denominator, back to the numerator, okay? So you have K Q over V0, which is C0. So in other words, once you do that, you are left with C, the new capacitance, is K, which is the, or this K would be different from the other K, by the way. This is the dielectric constant times the old capacitance of the capacitor. So if there is nothing between the plates, the parallel plates of a capacitor, then the value for the electric constant is 1. Okay, so C is epsilon 0 A over D. If there is nothing in between, and C, if there is something, is this. K epsilon 0 A over D would be, this is without, this is with the electric in between. So for example, if you put something like water, the dielectric constant for water, which is a huge number, is 80.4. So in other words, if you put a water between the two plates, you're putting a value of 80. So your new capacitance would be 80 times compared to the old capacitance. Okay? So depending on what you're using, you are changing the capacitance of the capacitor. Electric energy storage. Each of these capacitors are storing electric energy for us, because once they are disconnected, they can act as a source, or they can act as a battery, in fact. Okay. Sometimes you don't want to remove the source of energy or remove the battery, so that's why you're putting a capacitor in between. So once the battery is removed, then your capacitor is taking the charge and start pushing the electrons to move in the circuit. In other words, a capacitor is holding the energy for you. So that energy has a formula. The capacitor energy is half Q times V, okay, which is equals to half CV squared, which is equals to half Q squared over C. Remember, this relation is important. Q is CV. Okay, so if, for example, instead of Q here, you're choosing CV, you will end up with CV squared. Okay, if you make it to the power of 2, you have C squared over C, and then C squared, V squared is Q squared, and the C on the denominator is left. So there are 3 different formulas for it. I recommend remembering all of them. So energy has 3 formulas: half QV, half CV squared, and half Q squared over C. So these 3 are the most important ones. So we also have something called electric energy density. It has a number of different uses, okay? But if we divide the stored energy, so let me actually highlight this. If we divide the stored energy by the volume of the capacitor, so it has some sort of electric energy inside it, okay? For example, half CV squared, these are the formulas for those, right? Half CV squared, half Q squared over C, or half QV. If we divide that by the volume of the capacitor, then we have something called the electric energy density, right? the electric energy density right there. So we find the energy per unit volume, because if you consider the plates, they form you can find a volume that's been trapped between these two plates, okay? So that's one of your plates, that's the other plate. Then you can find the volume that is in between these. Okay, if you divide the electric energy by that, you will find the electric energy per unit volume. And the U of E is half epsilon zero, permittivity of the free space, 8.85 times 10 to the negative 12 times E squared. So finding capacitance, let's take a look at this. We have a 12-volt battery is connected to the parallel plate capacitor with a circular plate of diameter of 2.4 meters. So in other words, we have this. We have two plate capacitors that are circular, kind of like that. Okay, and they are connected to, the diameter for those is 12. So the diameter is 12 here. Let me change the color. So this is 12. They're connected to a 12, but this is, I think, 2.4 centimeters. And they are separated by a 1.45 millimeter distance. So they are connected to a battery of 12 volts. They are 1.45 millimeters away, and this is 2.5 centimeter. So this diameter is 2.40 centimeter, okay, which means that this is 1.2 centimeter, okay. This is what it means, that this is 1.2 centimeters. So what are we looking for? Determine the capacitance of the capacitor, okay. C is epsilon 0 A over D. So epsilon 0 is 8.85 times 10 to the negative 12. A is the area of one of these capacitors, okay, which is PR squared. Pi, R is 1.2 times 10 to the negative 2, because I want it to be in units of meters. Pi R squared. Okay, D is the displacement, which is 1.45 millimeters. Okay, so that's what the number is. This area is the area of a circle, which is pi R squared. Okay, so that's what the A is asking. So that's A. Let's go to B. B is determine the charge on the plates. So we're looking for Q. So Q is C times V. C is coming from part A. V is the voltage, which is 12. And then you can put it in the calculator to see what you can get. But then whatever this is, you can just use it right here, okay? And you can put this in a calculator to find it as well. And C is asking, determine the energy stored in the capacitor. So part C is asking the energy stored in the capacitor, U, okay, is half QV or half CV squared or half Q squared over C. You have all of them, you can find them. For example, if I want to do this, I would have U being equal to half. I know Q from part B, and I know V, which is 12. So all I need to do is to grab this guy from part 2 or from part B and putting it right here. Okay. So as I said, capacitors have a lot of applications, not only in physics or in engineering, in pretty much everything. If you open up a you know, electronic device, it is almost impossible to you know, find a spot without a capacitor. So there are everything that we use in almost daily life, they are all related to the voltage, and the voltages are all related to capacitors. And they are very useful. And you can probably search on this a little bit more, but I'm going to leave it like as it is. If you have any questions about this or the content of this chapter, let me know. And I'll talk to you guys soon.